In this course we're going to be talking a lot about electricity and magnetism, and before we get started I thought I should explain why this is important. And there are basically two reasons. One is because it's probably the area of physics most likely to get you a job, and secondly because it's the principles we're going to deal with, particularly vector fields, underlay huge amounts of fundamental physics. So first of all, why would this get you a job? Well, there's actually a principle in engineering that if you want to see the future, look at replacing mechanical objects with electric or magnetic fields. And this is certainly the case in all sorts of situations. For example, a touch-screen phone, they replace mechanical buttons with sensing of the electric field perturbation when your finger goes near. You take cars, you replace internal combustion engines with electric motors. You replace sending letters by surface mail with emails, once again electric fields moving. Lots of jobs involve things like working out the radiation pattern from mobile phones, setting up mobile phone towers, dealing with electrical interference in radios, TVs, all sorts of things. As for the more fundamental physics, most of what you've done in school in physics has involved objects. But when we get to electricity and magnetism, we're dealing with fields, strange invisible things that fill all of space. And these, it turns out, are the fundamental building blocks of most of modern theoretical physics. It's called quantum field theory for a reason, which is the best standard theory we have of particle physics. And so if you want to study grand unified theorems or where everything comes from, you're going to have to study fields. And a lot of the mathematics we'll do in dealing with electric and magnetic fields, things like vector calculus in particular, turn out to be fundamentally important for your quantum fields and Higgs fields and inflaton fields and all sorts of other fields that you get at the hairy end of theoretical physics. Now, electric and magnetic fields are examples of what are called vector fields. What is a field in the first place? When you first study electricity and magnetism, let's say electricity, you might have a charge over here and a charge over there, and you just use Coulomb's law to work out the force that this charge applies to that charge and vice versa. Now that's the simplest way to do things, but it turns out to be not quite correct. To make it work properly, you need to introduce a middleman, an extra feature. So the idea is not that this charge has a force on this one. What happens is this charge over here produces a field, an electric field that fills all of space. And then the bit of the electric field over here then pushes this charge. So instead of charge directly but mysteriously has a force that leaps through the vacuum to push another charge around, instead the charge produces a field and the field affects other things. A very important idea and one that turns out to be quite correct. It's called a vector field. So a field fills all of space. As I stand here, I'm in the middle of an electric field. Typically on the Earth's surface is an upward electric field of about 100 volts per meter due to static electricity in the Earth's surface. But anywhere in the universe you're going to be immersed in electric and magnetic fields and many other fields. But these fields aren't just a number, they've also got a direction. So what you've got to imagine is lots of little tiny arrows. So where I'm standing here, the electric field will be upwards. So you've just got to imagine lots of little tiny arrows showing that there's an upward, a vector, pointing upwards at all points, which is the electric field. Now normally if you have a positive charge, the field from it points outwards. You get arrows pointing away from the positive charge. They're very strong arrows nearby because the electric field is very strong. As you go further away, the electric field gets weaker, so you get smaller arrows away. But to the pattern, if you've got a positive charge, is electric field lines pointing away from it. If it's a negative charge, then you get field lines pointing towards it, small ones far away and big ones close in. For magnetic fields, it's a bit more complicated. Let's imagine my arm here is a wire with a current running towards my fingers. In that case, the magnetic field is going to go in circles around my arm. The way you work out how is use the right-hand rule. So I take my right hand and poke my thumb in the direction the current's going. The fingers curl round in the direction of the magnetic field. So if I really did have it going here, right hand like this, that means I've got the field lines pointing around like this. So those are the two basic patterns we're going to deal with. Electric fields, which point away from positive charges and towards negative charges, and magnetic fields, which curl around currents in a direction given by the right-hand rule. So remember, thumb in the direction of the current of your right hand, and then the fingers curl around to tell you the direction in which the magnetic field is working.